Thanks, Dustin. That was great and very wonderful. I wanted to add one other thing. Yeah, thanks. One other thing to the new additions. Let's see that. Oh, now I just spaced it out too. I should. Well, I'll come back to that as I remember it. Hopefully, Dustin had actually asked me late last year to talk a little bit about MIDCA and cognitive architectures and put it into context. There are a number of other cognitive architectures that have been in existence for over 30 years. A couple of them, SOAR and ACTAR in particular, go way back, and they're very mature and sophisticated. And I think we see some of that, and we call ours a cognitive architecture as well, but it shares a lot with it. But I want to try to highlight a little of the similarities and some of the differences with that. So I think one of the ways to think about cognitive architecture is to also consider other kinds of architectures. For instance, just a computer architecture, or even just an architecture of a building. We have a blueprint. Blueprints determine where rooms are, what the layout of a building would be, what its external structure is to the environment, but not things like where furniture goes for the most part. A lot of details then are populated by the owner of a house after it would be constructed. But the architecture defines the important structural things and functional aspects and the aesthetics for an overall design. Similarly, in computer architectures, we have a fixed set of characteristics. I do want to say that this is taken from the old Intel 8080. I think that was the original IBM PC was using that. So this is extremely old. Some architectures think of it a little bit differently now, but for instance, pipeline architectures. But here we can think of an architecture as containing functional components, and the 8080 shows a few of those. And then the data paths, how they're connected, which one provides data for others, and a representation for the data, and an instruction set to perform computation and changes. Then the user on an implemented chip or system that has come out of this architecture, a person would then be able to model something in the world and using a program or a language that then gets mapped to that instruction set and run under that architecture. So cognitive architectures are similar. They provide a fixed set of functional units, the connections, and often a representation in a language. We'll talk a little bit more about that and how some people have specifically described that. Excuse me. So there's also a number of other related concepts that we hear too. We hear not only cognitive architecture, but cognitive systems. And in fact, there's a conference that we published in a number of times called Advances in Cognitive Systems. They have a journal as well as a conference each year. I think the current one's coming up at Stanford, and it is the 6th annual Advances in Cognitive Systems. So what's the difference, between a cognitive system, cognitive architecture, information processing system, a cognitive agent, a goal-driven agent, or autonomy, reasoning? These are all related. So I will not focus on all of these, but some, particularly cognitive systems, it's a little broader. Pat Langley actually published in 2012 a really interesting paper. If you haven't seen it, you should read it. It's on the web and it's publicly available. He has defined 6 fundamental assumptions for cognitive systems that distinguish it from other AI systems. We go to AAAI, and there are a minority of papers presented on cognitive architectures or systems. Not all cognitive systems model from a cognitive architecture point of view, but they do usually assume that they're modeling high-level cognition rather than a low-level cognition, and often humans' intelligence rather than animal intelligence. So there's some differences there. Yes, a pause?
Sorry about this. This is we just need to change over.
So did that not get broadcast then, the slides? Okay, I can go back. That's still early.
Now they're seeing.
Okay. For those that missed, whoops, I'm going, hang on. All right, there was the architecture, related concepts, and then now about cognitive systems. So there were 6 basic assumptions that Langley outlined for the community. One was commitment to high-level cognition. Another, structured representations, often complex hierarchical representations. In cognitive systems, it's basically, it's not a bit vector or a simple vector of numeric values. Rather, it will be schemas or other hierarchical symbolic representations are the commonality for a cognitive system. Also, rather than optimizing, it is building a system that uses heuristics like people do. We often don't have complete and consistent, we don't do, well, let me see, I should just say often our solutions to problems as a human are good enough. That is, that they're satisficing and they get us through, they solve what we need in terms of a solution to a problem rather than the optimal perfect one. And there are reasons for that. But there's also a number of links to human cognition. Many of the cognitive architectures actually model human data, in particular. MIDCA actually does not have a big commitment to modeling human data per se, but it is inspired in many ways by human performance and human behavior, and has certainly a relationship there, but we don't model in particular data that would be collected from human subjects, for example. And the research is often exploratory in that certain theories, certain cognitive architectures have a theory of how cognition might work, and are exploratory in the fact that often they're early, well, it's not simply preliminary, but they're looking at a very complicated space and testing hypotheses in a way that often are not as formal, and they can be rigorous, but they're not often as narrow. They're broad hypotheses that test in more of an exploratory way. And I think this paper will explain that more clearly. Though there are a number of cognitive architectures, I'm going to list 5 here, and I apologize to many EPIC and many of the other architectures that are out there, but 5 that are I will briefly discuss today in terms of the relationship to MIDCA are ACT-R, which is out of Carnegie Mellon University, SOAR, University of Michigan, and it originally came out of CMU, Icarus at ISLE, and Clarion, Ron Sun, that's RPI, and MIDCA here. Icarus, as far as I can tell, doesn't actually have an acronym. I did want to mention too, SOAR, that was the original acronym, State, Operator, and Result. I believe that is no longer the case. They use it less as an acronym now, but I thought I would put it there for historical purposes. I want to broadly look at each very briefly and look at what their commitments to a cognitive architecture means in a very small way, usually through a quote. So I have listed in this presentation, I mentioned, I think the slides are going to be made available afterwards as well, but I've listed a number of publications that give you a little bit more details about what we're talking about, and some links to all of these architectures. The URL is provided as well. So back in 1991, there was a workshop or symposium at Carnegie Mellon that was held on architectures for intelligence. And there, I think ACT-R, SOAR were both presented, as well as Prodigy, and Tom Mitchell was there. I don't remember, Theo, I think, was the architecture. John Anderson had a chapter, the very first chapter actually in this book that came out from the conference, and he gave this principle of rationality. So his architecture, by the way, is Act R. It used to be Act Star, but the principle of rationality changed it. So the R in Act R stands for rationality. This principle is that cognitive systems, the adaptation of its behavior for the organism, whatever you're modeling. And so optimization is, well, yes, it depends on how you would define that, but essentially we adapt our behavior to learn and improve when things occur in the world. And he gives for the kind of for this principle, under this principle, when you're wanting to use a cognitive architecture, you first have this rational analysis. The first three steps are to specify the goal that you're trying to model for this cognitive system, the set of goals for the behavior that you're modeling with the architecture. You develop a formal model or a computational model of the environment that the cognitive system would be within, and make some assumptions about the computational cost, right? There's not only a cost to behavior, but there's a cost for thinking. And given those first three steps, you then derive a function for that, or a model in the architecture of that behavior. So your behavior might be planning, or your behavior might be text understanding, or it's something more narrow. For ACT-R, I believe they also looked at modeling human reaction time and memory experiments. So it might be simply memorizing a list of 5 words and then recalling one word that may or may not have been in that list after so many seconds of seeing it and then not seeing it. So that might be the behavior that would then be modeled. You then test that and either confirm or disconfirm the kinds of predictions that come from your model when you look at how people would do it. And if there is a discontinuity there, you would iterate and try to improve what your assumptions are, your formal model, what goals, how their goals are represented, or exactly what the goals are. You have ways to just iterate on that. Given that, then ACT-R has this kind of a structure. It focuses on memory in terms of a declarative and a procedural memory. Declarative memory being the memory for facts or concepts, or skills or behaviors, or how to do an action would be our procedural memory. How to ride a bike is less a step-by-step, well, I raised my foot by so much, it's whether I can just perform that. And so there's a long-term memory for both declarative and procedural, and that you can retrieve from or execute items from memory. You have a working memory from within. You do matching to your long-term memory to have to retrieve items for performance given some input encoding. There's a sensory register where the input comes from. So this is an abstraction too. There are a lot of details. The model is in a production system, or it's rule-based. You define the rules. That's kind of like the programming language for a computer architecture. Here you would define the rules for the behavior model that constitutes the behavior model. And then those rules would be matched from memory. You retrieve them and then execute the rules for behavior and see how it would operate given input from the performance. So now that touched on, he had a cognitive architecture. He talked about a cognitive system. There was a little bit synonymous. In a very interesting paper, though, later in 2009, that Anderson paper was 1991. Here, Langley and Laird, John Laird and Pat Langley and Rogers had a very good paper about cognitive architectures, and they defined it in terms of 3 characteristics an intelligent system, or for the agents. So the cognitive architecture specified a fixed domain independent infrastructure that consisted of memories, both the short and long term, memories that store knowledge or content about beliefs, goals, and knowledge. The representation, how those elements are actually represented in the memory for larger scale structures and how they're composed, and then the functional processes that actually operates on the knowledge um, that would produce an output given some input. So those are three important things I think you will find in all architectures, either more or less. For us that are in the MIDCA community and that are intimately familiar with MIDCA, we the representation, for instance, that we would have for a shop operator or for to create a domain. The documentation helps explain that. And we know Dustin went through the functional processes, but the memory model here is actually weak in MIDCA. But that is something I think that is forthcoming, where it's highly developed in most architectures and a large focus. Here we have SOAR model. You can see again a procedural memory in long-term memory, also semantic, and then episodic. So semantic memory is like an ontology, the concepts that we know about. Procedural, again, is the skills that we have. Episodic it's a memory of the actual actions that the individual performed in the past or currently, and we would store that. And it also has a symbolic working memory. It has a very sophisticated spatial visual system that has been connected with camera systems and robots in the past, and produces action. So there's a lot of similarity here. Unlike Act R, what is modeled is often not necessarily human data, and certainly usually higher level cognition and performance, for instance, on a robot behavior rather than reaction time studies. It's at a little different level than Act R, but there are a lot of similarities there. Icarus is also contains a number of the same things, a memory for concepts. This is a declarative memory in beliefs. It has a perceptual buffer as well. Skills here are distinct from concepts, but are represented in the same language or the same representation here. So there's it's slightly different, but very similar to the others that we've seen. Then there's a separate architecture definition by Ron Sun. He has a architecture called, but this is a very similar definition as well. He says that a cognitive architecture is broadly scoped, it's domain generic or domain independent. It's a computational cognitive model and captures essential structures and processes of the mind to be used in broad, multiple level, multiple domain analysis of behavior. So I think that is very consistent with what we've seen both in the principle of rationality, previous definition. Here, Ron Sun does distinguish, though it's not in this quote, it distinguishes between implicit knowledge and explicit knowledge. So I can show you that. This is Clarion. There are four main parts. There's an action-centered subsystem about behavior and skills and so forth. There's an explicit representation of actions and implicit representations. This is the upper left in blue. There's also non-action centered explicit and implicit representation. This would be for concepts, and instead of about behaviors, it could be about new concepts and learning facts. You would, for natural language, I believe that would be in this component. You also have a motivational system. Now this is the lower left, in which goals originate from. So there's both an explicit goals that are structured here, and there are implicit goals that emanate from drives of the system, basic drives. And then there is a metacognitive subsystem. So as Dustin mentioned, there is a commitment to metacognition also in this dual cycle architecture MIDCA. It is different here. The system, I believe, is subsymbolic or neural net based. The the implicit representations in Clarion are neural nets. The explicit are rules, again, like productions or a rule-based system. So there's still commonalities. There is this is one of the architectures, other than MIDCA and Clarion. I think few really look at metacognition specifically. What is done in metacognition here is, as I understand it, it's more about goal setting rather than originating the goals. I believe this is selecting the goals. It's similar to the intend function. More information can be found at the URL below at Rensselaer Polytechnic in New York. So I wanted to switch to our take on cognitive architectures and all of this cognitive agents and related concepts in the MIDCA, the little MIDCA community that we have here. And I can think of it as, my thought was to think of it as a perpetual goal-driven cognitive agent. We have less of, I mentioned, I have less of a commitment to human data per se, but more about agents that do things in the world, whether it's a robot or a model of a human. I don't think we're all about robots alone, even though, oh, and that was, by the way, the thing I forgot in the mini, one of the new things was the interface to ROS. I think that was really implemented this year. I'm not sure that we had it at last year's workshop. We did have it already by then. Okay, so I stand corrected. Anyhow, I did want to make a plug to it. But let me go back. If we're saying a perpetual goal-driven cognitive agent, what do we mean actually? Instead of a cognitive system, a cognitive agent, well, I would claim, well, actually, Hewins and Singh claims a cognitive agent is some intelligent system that uses knowledge structures, goals in an environment in which there's perception and action. So agents are ones that find themselves in some environment, whether it's a software or a physical environment. It may be a software agent rather than just a robot, but there's some environment rather than just mind games. It's embodied in some sense. And then goal-driven autonomy. There's a real commitment from this notion of what we call here goal-driven autonomy and more broadly goal reasoning in the MIDCA community. And I think this is one of the places where it started. And that's one of the focus of the metacognitive or the MIDCA architecture is that we don't just wait to be told. Agents, a MIDCA agent can generate their own goals given some anomaly that it would perceive. So it can recognize when there's a problem, possibly explaining what caused the problem, and then generating a goal to remove that cause. And there's some citations here that can point you to more about that commitment. But perpetual is simply just agents that would exist over long durations. And we've had some work. It would be, I think the ideal would be to have an agent turn on the robot and have MIDCA use it for a month. John Laird wanted to have a SOAR agent that had a memory of behavior over a year. And I'm not sure, but with the episodic memory that they worked on a few years back, they did have extremely long episodic traces or memories of continuous action. We have not done that kind of experiments like that, but we have put in place, and we, I think the the algorithms or the procedures, and certainly have thought about what it takes. That drives our research. It really, if you have a long for which an agent needs to be independent, things will happen that they don't expect in long durations, and you need to be able to react to that and manage it without to avoid catastrophe. Then this was the architecture. Dustin talked about it a little bit. I wanted to point out one very minor thing. I think his architectural diagram was from a little bit from last year. So in the perceive phase in the lower right in orange there, rather than claiming that this would be outputting a percept, I think within that, we would have a perception from the environment, and we generate out of perceive is a state in terms of predicate relations. If you're working with Ross in the environment, that's a very big problem, actually. Zora's, Danenauer's work has distinction there, and it's a minor one, but I just wanted to point that out. So as a cognitive architecture, as a cognitive system, or as an agent, I think these are the main points in which MIDCA makes the connections to other work in these related research areas. The 6 assumptions of a cognitive system, other than I had pointed out, it's a weak link to human data, more inspired rather than trying to model human data. I guess, well, that was in the principle of rationality, but the 6 assumptions for a cognitive system were generally met. It adheres weakly to the principle of rationality. We do focus on what the representation is and what the processes are, what the function of those processes are, that is their input and their output, and what is the transition, and but not memory per se. The 2 big points, how many minutes? The 2 big points, though, is that the MIDCA architecture really constitutes a computational theory of high-level autonomy, what it takes for an agent to be independent, generate its own goals, not wait to be told what to do. And secondly, it does center on goals and metacognition in particular, and I think that distinguishes it. But I can't emphasize more of the commonalities with it. These are the conclusions I think I've gone over, and to be on time, I just, Robbie, you can come on up. Just to reiterate, there's a lot of commonality here, and we do share with all cognitive architectures. We differ. There were a number of examples that we covered, and hopefully we will have coming out in this following year a version 2 of MIDCA. We shall see. Thank you.